Okay, so today we're starting our last unit. Isn't that so sad? You probably don't think so. But we're starting the final algebra unit, which is going to be on quadratics. We are not actually talking about quadratics today, but what we're talking about today is going to help us when we get into the quadratics tomorrow. So what we're looking at today is how to factor. We saw a factoring lesson in pre-algebra forever ago, so you may remember it, you may not. If you don't, it's all good because we'll review it, what factoring means. But you did see polynomials last quarter in algebra, so we're going to be using some of the stuff you learned about polynomials to help us factor with GCF. Do you know what GCF is?
No.
It's all good. We'll review that too. We are going to start off, though, with reviewing something you do know how to do, which is distributing. So this is something we learned back in algebra. Or I mean, we are in algebra now, but back in Algebra 1A last quarter. I'm hoping you remember how to do this. So I'm going to have you go ahead and try those two, okay? Got something? Oh. So earlier on that do now, I heard you say for that division problem, you said, I remember when you're dividing, you subtract exponents. What did we have to use for these? When we're multiplying, you add the exponents. So for this one, when we multiply, we end up with
6x3
cubed.
cubed minus 12x squared.
Yep. And then the really fun looking one.
We can do 14x squared.
Nice.
Y to the fourth plus 8 x cubed y to the sixth minus that'd be 20 x and then y cubed.
Nice. It was also practice on how you read all this stuff. Perfect. So you already reviewed for me when we're multiplying, we add our exponents. I noticed for this last one, you flipped it around. How else could we have written this?
The y could have been before the x.
Yep. So for all of these, you could have those variables in a different order. They mean the same thing. The reason I wanted to review this is something we learned back in our polynomial unit. We learned how you get from something that looks like this to something that looks like this. Same idea here. We just called that multiplying polynomials. What we're learning today with factoring is how we go from this to this, or how you go from something like this to this. Factoring and distributing are opposites. The idea of factoring is taking something that isn't a multiplication problem. This is just a bunch of addition and subtraction, and changing something to look like multiplication. There's going to be a couple different ways we learn how to factor. The way we're learning today is using something called GCF, which says greatest
Common factor.
There we go. It was buried back in your brain. So this is just going to review what we said here. Factoring is rewriting something as multiplication. And just looking into the future, we're not rewriting something as multiplication just for fun. This idea of being able to rewrite something to look like multiplication, it actually can help you solve a lot of different things. So that will be something you see next week. But there is a purpose, there is a reason why we're doing this, in addition to it being fun. So we're going to be factoring, it's rewriting something as multiplication. We said the one way we're going to factor today is using GCF, which you remembered stands for?
Greatest common factor.
Yep. When we say greatest common factor, oftentimes when that is first introduced, it's introduced just with numbers. So for example, if I have the number 15 and I have the number 20, when we say greatest common factor, the greatest common factor is the biggest number that goes into both 15 and 20. Another way you can think of it maybe is like the biggest number you could divide both of them by. So it has to be a number they have in common. So for example, for 15 and 20, the GCF would be
5.
Nice. 1 also goes into 15 and 20, but 1 is not the greatest. 10 goes into 20, but it's not a number in common because 10 doesn't go into 15. So this idea of greatest common factor, this is what it looks like with numbers. You already got like an idea of what we're doing today though, is it's also going to have variables in it. We're going to find what the greatest common factor is, including like what variables they have in common. So with that, we've got some examples we're going to look at. Each one of these is a polynomial that we are going to change to look like multiplication. From that example we saw a moment ago, what you might have noticed is there's going to be one set of parentheses and there's going to be something in front. And the goal is when I multiply whatever's in front to what's inside, I should be getting this. That part that's going to go outside, can you guess?
The greatest common.
Yes. So our first step is going to be figure out what that is. When you look at these two numbers here, do you know what that greatest common factor is?
3.
Perfect. If at any point you don't know what the greatest common factor is, you can always make factor lists. What that looks like is just writing all the different multiplication problems that give you 6. For example, for 6, we could start off with 1 times
6.
1 times 6, and then just keep going up. So 2 times 3. If I did 3 times
2.
which is already listed. If you're going in order, that's how you know you got them all. For 9, it would be 1 times 2 times
4.5.
Ooh, yes. So when we're writing those factors, we're looking for those whole numbers. So you were right to give me that weird face. So there's no 2. 3
times 3.
Yep. And then we've completed it. That greatest common factor is the greatest number on both lists, or the greatest number both lists have in common is another way you can think of it, which is the same thing you told me. This one with the numbers being smaller, hopefully it's safe to say it's fairly easy, but if I made it like 64 and 91, doing something like this might be helpful. So you said 3. There's something else they also have in common.
X.
Yeah. Now when it comes to the variable, sometimes it has an exponent, sometimes it doesn't. One way you can think of it is this is saying there are 2 x's there. This is 1x. So what we want to say is, well, they both have at least 1x. Do they both have at least 2 x's?
No.
No. So this is it's the greatest number of x's they had in common. If this had been 9x to the 5th power, what would the GCF look like?
We would have I don't know the word, but it would have a,
Exponent?
yes.
What would that exponent be?
Um, 2. 2 times 5. 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 2 times Because it would have to be at least 2.
Yeah, they both have at least 2. If this had been 20, then we would say they both have at least
5.
Notice every single time we're picking the smaller exponent. We can't go with the bigger number because they both don't have this many, but they both have at least whatever the smaller number is, which is the other way you can think of it. We've got our greatest common factor. For the last part, tell me what you're thinking for how we're going to figure out what goes inside.
Well, it would be 2x plus 3.
How did you figure that out?
Because when you distribute 3x into those,
Mm-hmm.
you'd get 6x squared plus 9x.
Yep. So one way you can think of it is thinking of like, what do I need to multiply this by to get 6x squared? So you could ask yourselves like 3 times what gives me 6? Well, I know 3 times 2. X times what gives me x squared? And do it like that. The other way you can figure it out, instead of thinking like what I need to multiply it by, do you know the other way?
Which you could divide it by?
Yeah. So using what we've got up here, 6x squared divided by 3x gives me 2x. 9x divided by 3x gives me 3. So because multiplication and division are opposites, it just depends on how you think of it. Sounds like you're thinking of it this way, like what we need to multiply by. It's also the way I do it. So that's probably the way we'll end up doing the rest of these since you are the only student. But people at home, if you like division, you can also use division. For each of these, the last part of this, you know my favorite word in math, we could check these. How do you think we could check these?
I guess you could do the opposite of what you did. Like if you multiplied, you could then divide.
Yeah. When we're factoring, we're not changing the amount of it. We're just changing the way it looks. These two things should be equal. So what you said by multiplying it out is a way we can check. We could multiply this out, and what are we expecting to see?
The same answer.
Yep, this thing right here. So when you do check, I encourage students to like cover up what the goal is, because you want to do like a proper check and not be like, oh yeah, I should get 6x squared plus 9x, and look, I do. So if we pretend that's not there and actually multiply this out, 3x times 2x.
The 6x squared.
I am not right-handed. And then 3x times 3.
The 9x.
Could have been worse. And then we check and see, yes, that is what I was going for. I've got a lot of stuff written down here. What is that final answer? If I ask you to factor this, what is the factored form?
It is the multiplication.
Good. It's this right here, specifically because what you just said, that's the multiplication part. When we're factoring, we're changing it to multiplication. I asked that question because there are students who love checking as much as I do, which makes me very happy. But once they check, they put this as the answer. Why is this not the answer?
Because that's not the factored form.
It's not the factored form. It's also the problem. So this would be like me saying factor it and you saying no. So make sure, I just want to check to make sure you know what that factored form looks like. We've got 2 other ones we'll do a lot quicker, I promise, and then I'll give you ones to try. This one here, talk me through. What do you think we need to do first?
Well, you need to find the greatest common factor.
Love the vocab.
For 10 and 15 is 5.
Mm-hmm.
And then there's an x to the 5th and an x to the 4th, so you can just do x to the 4th.
Mm-hmm.
And then you can do y to the 2nd. And then that would be what you have before the parentheses.
Okay.
And then before the parentheses, 5 times something that equals 10 would only be 2.
Mm-hmm.
And then there would be an x there because you only have x to the 4th. And then there would be no y with that.
Mm-hmm.
And then plus 3. And then, oh wait, no, so it would be just y, not y to the 2nd.
Tell me how you figured that out.
Because you can
Good. So back here when we were finding that greatest common factor, you had 2 there. This is part of the reason why we're going with what they have in common, is because if you put too many out here, then you're in trouble here when you're trying to just have y, and you've already got y squared out. So we're going to be careful. If I change that, it's going to change something else now.
So instead, the 3 would have a y with it.
The 3 would have a y with it like that?
Yes.
Okay. So let's check. I'm going to cover that up.
Oh. So the 2 also has a y with it.
The 2 also has a y with it. Okay. Let's still check.
Okay, so 5x to the 4th y times 2xy would be 10x to the 5th, and then y to the 2nd, plus 5x to the 4th y plus, or times 3y would be 15x to the 4th y to the 2nd.
Y squared. So you've multiplied it. Let's check and see. Is that what we were looking for?
No.
What's wrong?
Okay, so so there should be no y with 3.
Yep. This is a beautiful example of why we check. Because in checking it, you realized pretty quickly too. You went, oh, okay, wait. As soon as you see that check, if it does not look the same, you know something's off. And the great thing about it, how did you know it was the y so quickly that we had to change?
Because if there's 2y, you get y squared, and
Yep.
that is not the original thing.
Yeah. So that check is showing you where the problem is too. It's not just like, oh, I know something's wrong, but I don't know what's wrong. If that's the part that we need to fix, it tells you that's the part we need to fix. Everything else looks good? Yeah. Okay. This last one here, there's 3 terms now. The idea is the same. When we find our greatest common factor, what will that look like?
Well, there are negatives, but I guess that doesn't do.
We'll talk through the negatives. I'm glad you're noticing that. What about the rest of it? Our greatest common factor, what would the number be?
Be 2.
Why 2 and not 4?
Because there's a 2 at the end.
Yep. So you're finding the greatest common factor of all 3 numbers now. So you've got our 2. What else?
Okay, so then it would be just a and b.
Just a and b. Why no exponents?
Because the smallest exponent is 1.
Yep. This last one here, they both only have 1, so we can't take out more. Now you had noticed that there's negatives in it this time, and there is a rule that has something to do with negatives, so I'm glad you noticed that. The rule we're going to follow is if the polynomial starts with a negative term, not necessarily if they all have them, but if there's this first one here is negative, that means we are going to make the GCF negative. There are multiple things you can write. Multiple multiplication problems you can write that equal this. You could put a negative sign here, you could put a positive sign here, and still have something that equals this. So to create a rule so we all have the one same answer, the rule is if it's positive, your GCF will be positive. If it starts with a negative, our GCF will be negative. Once we know that, I think you can finish it now.
Okay, so you'd have to do 2 a to the 3rd plus 4 a to the 2nd minus 1.
With these negative ones, those signs can be tricky. Can I hear what you're thinking when you're saying like plus and minus?
Because if it was minus 4a to the 2nd, then you would be negative times a negative, which would be a positive, and that's not what the original.
So what I hear you saying is you're thinking through the rules, like negative times what sign would give me a negative. Negative times positive would give me a negative. That's perfect. Again, if there's anyone at home watching this who likes division, the other way you can think of it is a negative divided by a negative gives a positive. A positive divided by a negative gives a negative. You're just going back to those negative rules we know. We've got that one. I'm going to be here to tell you that the check is all good, just because I'm trying to be mindful of time. So these were my examples. You have 3 on the back side for you to try. We said we were going to get you out of here by 2:30, right?
Yeah.
Okay.
I think I only need to do that for like this week. Because,
For the training?
Yeah.
Okay.
Because I think when I actually start, I'll be doing it like 6 at night.
Okay. I was like, wait, in the morning or the afternoon. Okay. All right, that works. Also try to make sure we get you all done by 2:30 though. Did I switch? Yeah. I like how your GCF is negative. Think of the greatest common number between 5 and 10. Yes. But maybe check that first one by multiplying or so if you are at home for this first one, you want to find the greatest common factor of 5 and 10, which would be 5, because this first term is negative. That means our GCF will be negative. When we look at our variables, they both have at least 2 z's. I'm going with the smaller exponent, so that'll be z squared. When I ask myself, what do I have to multiply that by to get here? Negative 5 times 1 gives me negative 5. Z squared times what gives me z cubed? Well, I'm going to need one more z. Negative 5 times what gives me negative 10? Well, negative times a positive gives me negative. 5 times 2 gives me 10. And then z squared times what gives me z squared? Well, I don't need any more z's because I already have all 2 of them. So this right here would be our answer. You've got beautiful. For this one here, notice I asked a different question and asked what's the greatest common factor. Tell me what that greatest common factor is.
Be 8, and then x to the third.
X.
Cubed.
Yes. X cubed, and then
Y squared.
Y squared. Great. You did an excellent job if that's all you wrote. If I'm asking you to factor something, that's when you're doing all of this. If I'm just asking for the GCF, the greatest common factor, that's just what goes in front, which for this problem would be this. And then you've got that last one correct. Will you give me the answer for anyone watching?
2pq is the greatest common factor.
Mm-hmm.
And be 5p minus pq plus 1.
Like that?
Minus 2pq.
Okay. I was like, I think I saw 2 on your paper. All right. The last part of this is more factoring. But there's something different about these here. When we look at this first one, we've got 15xz to the fourth power minus 20z squared. The idea is the same. We're going to factor it with greatest common factor. Where do you want to start?
Well, greatest common factor would be 5,
Mm-hmm.
and then x z cubed, or squared, I mean.
Xz squared. And then parentheses?
Yeah, parentheses. And then it would be 3z squared.
Mm-hmm.
Minus 4. Oh, wait.
But wait. I love that sound, but wait. But wait, what?
The greatest common factor can't have an x in it
Why can't it have an x in it?
because the second number does not have an x in it.
Yep,
So
the second term doesn't have an x. So that's what's going to be different about these, is those last ones, each time all of our terms had the same letter, the same variable. But here I'm checking, you've got to check and see if it's actually something they have in common. So you notice, wait, it's not. This one doesn't have an x. So we take that out. How is that going to change what we have over here?
the 3 will have an x with it
Good. Where do you want that x?
in front of z.
Does it matter?
No.
There you go. Do you want an x over here?
No.
Why not?
Because it does not need it.
How do you know it was not needed?
Because the, what is it? Because the question doesn't have an x with the second three.
I'm curious what word you're trying to look for. The whole thing is called an expression. The second part here, like this whole thing here, is called a term. This number here is called an exponent. Were any of those words the word you were looking for?
No, I was thinking of like what that is called because we're doing the factoring. So
Oh, what this part here is called?
or no, like the actual. Like,
This here?
question. Yeah.
That whole thing is called expression.
Yeah. I don't know. What I was thinking.
I think the word I probably would have used as like term is saying that second term doesn't have an x in it, so we don't need an x here. But it was a great review of all of our vocabulary. Once we've talked through that idea a little bit, these two should be quicker. This one here, greatest common factor.
3. But it would be -3.
Mm-hmm.
And then you'd have x to the 4th. And that is it. That's the common factor.
Okay.
And then you would have 3x y squared z minus 5w.
Nice. I think you got it. Do you want to try this last one? Oh, we could do it together. I just meant on your paper, but you can. Do you want to tell me? I'll write it up here for you.
Would it be 1?
It would be 1.
And then, see, you'd be 1a. Or just a.
Yep. Nothing wrong with 1a, but this is how you're going to see it.
And
Just
then
a? That's it.
Parentheses. You have 3a cubed b minus 7a squared b plus 2.
Yep. It's like going through all of these and just taking out 1a from everything. Everything else is staying the same except for the a's. The exponent's just going down 1. Nice. You feeling better about these?
Yes.
Okay. There are 3 for you to try. Want to see?
Okay.
Let me check this last one. What? Start with your GCF.
Be 4J.
4J. And then what do we have in parentheses?
You'd have 3J squared, cubed. And then K to the fourth
Mm-hmm.
minus M
Nice. We've already got the 4J out here, so we just need the M. And then
plus 2J squared K squared.
nice. Right, and I checked yours there. I'm instead of ending with that question, I want to end with this question here. It's kind of changing what we're doing. Instead of me giving you a polynomial and asking you to factor it, I am giving you what I want the greatest common factor to be, and I'm asking you to write a polynomial. So your answer is going to look like one of these here. It's like doing the opposite of these problems. Tell me what you're thinking. How would you approach that problem?
Because the greatest common factor is 6x cubed,
Mm-hmm.
you can basically do any multiple of 6,
Mm-hmm.
and then with x cubed in there, but like x with a greater number than 3,
Ooh.
and then potentially anything else if you wanted to put it in there. So you could do like, so the GCF is, so if we're just trying to get the polynomial,
Mm-hmm.
you could do like 12x to the fourth.
I'm going to do it a part at a time. I can tell, like, you know what you're doing, but I'm just going to break it down into steps. So the first thing I heard you say is because the GCF is 6, we want to write down some things that are multiples of 6 is how I heard you phrase it. So 12 is a multiple of 6. What else?
Plus do like 18.
Sure.
Do like,
How many terms do you want? Do you want 2, 3, 12?
well, because it's a polynomial, it has to be more than one.
Yep.
You could do like 3
Sure. 12, 18.
and 6.
That would work. When it comes to doing the multiples, this is perfect. You want to be careful that when you're writing those multiples down, you don't give it a bigger greatest common factor. So what I mean by that is 12 is a multiple of 6, 24 is a multiple of 6, but the greatest common factor of 12 and 4 isn't 6. Do you know what it is?
It's 12.
It's 12. So I like exactly what you did, and sticking the 6 in there is going to help guarantee it's not something too big. But it's always good to do like a quick check. So that was the first thing I heard you say earlier, is you said we want multiples of 6, and then you said because the greatest common factor is x cubed. What were you saying about the exponents there?
The exponent has to be at least x cubed,
Mm-hmm.
more, but it can't be less.
Good. So it's got to be at least x cubed, at least a 3. Could be more than 3, but not less than 3. So we could say,
Like that one could be like x to the third, and then you can just like throw a j in there or something.
ooh, making it fancy.
And then plus x to the fifth plus x to the ninth.
Perfect. You're truly meant to be a math teacher. I think it'd be like we could throw in another variable too. What do you think the warnings I'm going to give about throwing in other variables? If we put a j here, what do we need to be careful about?
I'm not sure.
Could I put a j here?
Yes.
Could I put a j here?
Yes. Maybe. No. Because then the greatest common factor would be 6x cubed j.
Yes, exactly. So this was the only spot you told me to put a j. We could have also put it on another one if we wanted to, but you got it. We can't put it on all of the terms because then it would turn into something they have in common, which would then mean that would be our greatest common factor. So feel free, if you want to have fun with your variables, you could put some n's for Nile in there if you want, but you just can't put it on all the terms. this is beautiful. If this was a little too fancy for you, you don't have to go with 3 terms. You could do 2 terms. We could say, like you were saying, multiples of 6. So you could do 6 and 60. And then for that variable, x cubed, like you said, we need at least 3 x's for both terms. We could have x cubed, and then over here we could have
x to the 5th.
Sure. Polynomial? Good. This was a beautiful example. But multiple examples are always good. That is a good place to end it on. If you can do something like this, like I said, I can tell you understand what's going on. It's a good indicator you understand what's going on over here too. Nice job. It's like perfect timing. Yeah, this is a good stopping point. Goodbye, people at home. And